So it's my pleasure to introduce Jeff Hirst, who's going to talk on 3 views of LPO and LLPO. Thank you, Jeff.
So thanks for inviting me. It's a great pleasure to come in and talk to you in the Midwest, no matter where you're arriving from. And I wanted to talk through several different ideas related to these 2 principles, LPO and LLPO. So let's take a look at LPO. So LPO is the limited principle of omniscience, and this is a principle that's discussed a lot in constructive mathematics. And the basic idea is this: if you have some function that's essentially a string of zeros and ones, then zero's in its range or it isn't. So we could formulate this as some sort of an AE statement where we said for every string that somebody gave us, we could pick out a natural number that's 0 or 1, and we'll make it 0 if 0's in the range, right? So another way to describe this notion of LPO is to construct a Buyroute realizer for it, which would be a functional, and we'd input the string f, and then the functional would output 0 or 1 depending on whether or not 0 was in the range of f. Okay, so this is just some functional. It's not necessarily a computable functional, and it's not. So let's compare LPO to LLPO. Okay, so LPO is a weaker principle called the lesser limited principle of omniscience, right? And it also, you feed it a string, right? And it looks to see if, well, if 0, it turns out to be in the range of the string, so it appears someplace in the string, then LLPO will tell us whether the first 0 occurs at an even location or at an odd location, right? So again, we could write this as some sort of an AE formula. And here, the AE formula is actually just an implication. So if 0 shows up in the range someplace, then the value that we get is going to be 0 or 1, depending on whether or not the first location where 0 appears is an even location or an odd location. So if I wanted to think about a realizer for LLPO, right? If my string looked like this in this top string, then the first 0 appears at position 2, and that's even, so we would output 0. And in this next case, well, the first 0 showed up at 3, and that's odd, so we'd output 1. So those are very straightforward. If we look at this next example, we kind of say, well, we don't know what's happening here yet. You know, we've only looked at the first 5 places, so that the output could be 0 or 1. The realizer will give us one or the other, so it'll output a 0 or 1, even if the string turns out to be an infinite string of 1s. So if there's no 0 at all, then the realizer would have sort of the option of giving us any kind of output it saw fit to provide, right? So this is kind of interesting. In the situation with LPO, there would only really be one possible realizer. But when we look at LPO, of course, there are many, many different realizers that you could have here, depending on the behavior on the string of, well, I guess 2 realizers, depending on the behavior on the string of all ones. So the first place that I really ran into these principles of LPO and LLPO was looking at things related to Buyroute reductions. And I wanted to talk a bit about Buyroute reductions here. If you're a person that works in this area, you could take a little nap now while I explain what I mean. And the way that I usually think about Buyroute reductions is in terms of problems. And if I had two problems, P and Q, then I would say that P is reducible to Q and write P is less than or equal Buyroute Q. If we could find a couple of partial computable functionals, phi and psi, that have an interesting relationship to these problems, right? So if you start with P being an instance of the problem P, then phi of P takes that instance of the problem and turns it into a Q problem, right? And then if we take this Q problem and any solution of it whatsoever, psi is supposed to take that solution together with the original P problem that we were given and give a solution to the problem P, right? So it's kind of nice to think about these in terms of realizers. So if I had a realizer for the problem Q that would take Q problems and provide a solution to them, then I look at this mess, right? So what is this? I'm going to take phi of P, that's going to turn it into a Q problem. Then I apply the realizer and that gives me a solution together with my original problem. And psi is supposed to spit out a solution to P. So this composition of functions is now going to be a realizer for P. Now, sometimes when people do Buyroute reduction, they say, okay, psi here gets to use this information about the solution, and it also gets to use the original problem. What if we don't use the original problem? So the only information that we have is the solution to the Q problem. Could we still compute the solution to P? If you can do that, then that's called having P be strongly Buyroute reducible to Q, right? So that's basically when you say strongly, you just leave this P out of the input for psi. So this is a repetition of the sentence that we were just looking at, where you have this composition, and that turns out to be a realizer for P. In terms of like thinking about these as computations, I usually think of phi here as being a preprocessor. So you take your P problem and run it through the preprocessor, turns it into a Q problem. And then psi is some sort of a post-processor that takes the P problem and an additional input, right, and produces a P solution, right? And the idea behind Buyroute reductions that I think is really interesting is phi and psi are supposed to work for any Q realizer that we come up with, right? So you just plug any Q realizer in here, you'll get a P realizer out every single time. So there's a certain uniformity in Buyroute reductions that's actually kind of an issue that will show up later. So let's look at an example of a Buyroute reduction. So what I'd like to do is show that LLPO is Buyroute reducible to LPO. So this is I don't even know if it's a folk result. I'm not sure, who originally wrote this down. Yeah, probably Buyroute, right? So here's one way to do it. We can do it relying entirely on the post-processing part of the computation, right? So for the pre-processing part, right, we'll just take the LLPO problem. So you give me a string for LLPO, right? And then I'm going to not do anything to it and just pass it through, right? So this is a null process. We just do nothing and go on, right? And then what we want to do is use LPO and do the post-processing, right? So we're going to input that string that we just got from not doing anything during the pre-processing, right? And apply LPO, or realizer for LPO, to the string, right? This is still really just P here, right? And so this is going to give us the LPO solution for our LLPO problem, right? So we're trying to figure out in solving these LLPO problem, whether the first zero, if there is one, is in an even location or an odd location. And at this point, what we've got is we took the string and we know whether it has a zero in it or not, right? Well, if it doesn't have any zeros in it at all, so P was a string of all ones, right? We'll just say, okay, the first zero appears in an odd position because we can say anything we want, right? And halt, right? So that's a perfectly good output for LLPO. And if on the other hand, the LPO process tells us, well, there's a zero someplace in the string, right? Then what we'll do is start parsing down through the string until we find that first zero, and then we'll output the location mod 2, right? So if we wind up in an odd location, we'll kick out 1, and at an even location, we'll kick out 0, right? And so this works okay. There's a little bit of an interesting twist here because this post-processing algorithm is partial, right? So if somebody gives us false information about the string, right, then it could be that we'll generate incorrect output, right? Or not generate any output at all, which is really what the issue is, right? So if somebody tells us, oh yeah, there's a zero in this string and the string is a string of all ones, then we're gonna drop down here and start searching down the string and never produce any output. So yeah, this is a partial computable post-processing algorithm. Okay. So this isn't the only way that you can show that LLPO is Buyroute reducible to LPO. And it turns out that another way to go after this is to concentrate on the pre-processing and then sort of ignore the post-processing, which is an interesting twist on the algorithm, right? So if you want to do that, we need to talk about how to do the pre-processing. So somebody hands us some string of zeros and ones, right? This is an LLPO problem. I want to figure out whether the first zero is in an even location or an odd location, right? So I'm going to build a new string. And for each n, what I'm going to do is just look at previous values of the string that I was given, the string P, right? And if I look at those previous values and I see a zero appearing there, and the first zero that appears is actually an even location, then I'm going to make Qn equal to 0, right? And otherwise, I'm going to make Qn is equal to 1. Right? Now, it's interesting to think about what happens if somebody gives us a string of all ones, right? If they give us a string of all ones, then we go through this process and we wind up with a string of all ones. If somebody gives us a string and the first zero in the string is in an odd position, then this part never holds and we get a string of all ones, right? If somebody gives us a string, a P string, and the first zero is an even position, then we're going to catch here, right? And we'll have a 0 in our string, right? So then when I take that and run it through my LPO realizer, right? When I apply LPO to the pre-processed string, I'm going to get a 1 if and only if, well, I get a 1 if the first 0 appears in an odd position. I get a 0 if the first 0 appears in the even position, right? So actually just R LPO, just R of the pre-processed string gives me the output that I desire for LLPO, right? So in the process for psi, right, I don't actually have to do anything, right? The input here was supposed to be the string and the result of this applying this realizer, right? And I'm just outputting the realizer and throwing away the string. So this is actually a strong Buyroute reduction of LLPO to LPO, right? And the other thing that's kind of interesting here is that phi and psi are both total, right? So we aren't looking at partial pre-processing or post-processing algorithms. So one other thing with Buyroute reducibility that we can look at is parallelization of the problems. And the notation for parallelization is this hat notation. And the idea of p hat is that you input an infinite sequence of p problems as the input, and then output the sequence of all of their solutions, right? So let's think about doing this with LPO. So we're going to input an infinite string of LPO problems and output all of their solutions as a string, right? And we could write this in an A formula like we were doing earlier, right? And so the idea here is if you have any string of inputs, then there's a string of outputs, and each output is either 0 or 1, and the output is 0 if and only if the associated function has 0 in its range. So if you look at this sort of a statement, this kind of a AE statement, where for every set of one sort, and you could code this just as a set of natural numbers, and then we have another thing here that we could code as a set of natural numbers. So this is actually some sort of set existence statement. So if you were someone who had been deeply influenced by Steve Simpson and Harvey Friedman, you might say, well, that looks like reverse math, right? And that's because I like to think of it like reverse math. So let's talk for just a few minutes about the base theory. So reverse math, the whole goal of the program is to measure the strength of theorems by proving equivalence results over this base theory of RCA Not. Very roughly, the base theory has variables for natural numbers and sets of natural numbers. So if we were type theorists, we might say it type 0 objects and type 1 objects, right? And then it has some arithmetic axioms. So the usual sorts of things that define, for example, the behavior of addition, multiplication, and so on. Induction restricted to sigma 0, 1 formulas, and then a recursive comprehension axiom, which very naively asserts that if you can compute a set, then it exists, right? Actually, it probably would make more sense to call it a delta 0, 1 comprehension scheme, right? But from a naive viewpoint, this certainly works. And in actual practice, I think most of us that do reverse math think about things this way, right? We go, oh yeah, I can compute that, so it exists in RCA Not, and move on with our lives. Okay. So the goal of having this base theory is that we can prove that many theorems of mathematics are equivalent to one of 4 set existence statements, one of 4 additional axioms over RCA Not, right? And the source here is actually to Friedman's original abstracts. It's interesting to go back and look at those and see, how many things he had already fit into these categories, even at that point, before the program really got underway and had many participants. So the question for me is, okay, we were just looking at LPO hat, and we said, oh, we can write this as some sort of AE statement, which is a set existence statement. So where does this fit in this hierarchy, or does it actually? Okay. And it's not too surprising that it fits at the level of Aca Not. Okay. And part of the reason why it's not surprising is if you think about the reversal here, so the proof from LPO hat to Aca Not, right? What we can do is look for, we can prove a statement that's equivalent to Aca Not. So there's this lemma that is often used and you can find in Steve Simpson's book, that Aca Not, this arithmetical comprehension scheme, is equivalent to the existence of ranges for arbitrary injections, right? So how would we turn that into a sequence of LPO problems? Well, for each LPO problem, we could say, okay, for my 0th LPO problem, I'm going to figure out whether or not 0 is in the range of my injection, right? So I start evaluating it. And if at some point I find that my injection has 0 in its range, in my 0th LPO instance, I will insert a 0 at that point, right? And have ones leading up to that point and then 0 at that point. You could continue with zeros from that point on if you like, right? And then when we run that through LPO, LPO is going to give us a 0 if there's a 0 and a 1 if there's not. So that you can think of this as being, I guess, the flip of the characteristic function for the range of our injection. Okay. So we could ask the same question and say, well, where does LLPO hat fit now? We were saying earlier that it's weaker than Aca Not. So how weak is it? And here, this is not is also something that's not terribly surprising. That WKL Not is equivalent to LLPO hat written as a set existence statement, right? And the thing that kind of motivates this again, if we want to think about the reversal here, one of the common things that's used for reversals to WKL Not is to separate the ranges of two injections that have disjoint ranges. So we look for a set that contains the range of one function and not the range of another. So again, we want to make a sequence of LLPO problems. So maybe for the 0th LLPO problem, we're going to start looking at the ranges of the two injections, right? And if at some point the function shows up in the range of one, or the 0 shows up in the range of one injection, but not in the range of the other one, then we'll rig our LLPO problem so that it'll output 0 or 1 by putting a 0 in an odd or even position in that instance of LLPO. So it's pretty easy to turn a problem like this, where we're trying to separate two injections, into a sequence of problems, a sequence of LLPO problems. So I think there are some interesting computability theoretic observations to make at this point, right? One is that we know that there's a computable injection on N with a range that computes 0 jump, right? And consequently, we can use the ideas from the reversal that I was telling you about a few minutes ago to show that there's a computable LPO hat problem, so a sequence of LPO problems such that every solution to the entire sequence would also compute 0 jump. In terms of omega models for these subsystems, it's true that there is an omega model of weak Kernig's lemma that consists only of low sets. So every set in the model is a low set, right? So some set A such that A jumps equal to 0 jump. And that tells me that if I have some computable LLPO hat problem, right, it would have a solution in this model. So it has a low solution, right? So LPO hat can't be Buyroute reducible to LLPO hat, because if it was, then I could use my postfix operation to turn this low set. I could use the post-processing operations and apply it to the low solution to the LLPO problem and actually compute 0 jump. So I could compute 0 jump from a low set. Right? So this tells us that we don't have a Buyroute reduction of this sort, right? And consequently, LPO can't be Buyroute reduced to LPO either, right? Because if it could, then you can put hats over it. Hats preserve Buyroute reducibility just by compositions of the pre and post-processing algorithms. So lately, Carl Mummert and I have been talking a lot about higher order reverse mathematics, and sort of our framework for thinking about this is this article by Kohlenbach from the Reverse Mathematics 2001 book, where he set up an extension of the axiom systems to handle objects of all finite types, right? And one of the things that Carl and I had been talking about is how we can look for equivalences between different statements, which are essentially skolemized function existence statements, right? So let's look at an example of something like this. So if we look at LPO, right, where we say, okay, for every string like this, you have some number, right? Then we can look at like a skolemized version of this. So something that's supposed to take the F as an input, right, and output the desired N, right? So that thing, in this case, it's going to be a realizer for LPO, right? So we could just say, oh yeah, there's a realizer. So this is just the Skolem function for this AE statement, right? And we're saying here that the Skolem function picks out an appropriate N. Okay. So I guess there's a couple of things to talk about here. For one thing, the Skolem function is something that maps strings, infinite strings, to natural numbers. So we're kind of outside the area of sets at this point. We're mapping sets to natural numbers. So this would be a type 2 object, right, or third order arithmetic rather than second order arithmetic. And consequently, in order to write these things down and have them work in our axiom system, we need to move to higher order reverse mathematics. The notation here is a little bit loaded too, right? What I had here was the statement that I was calling an LPO before, and I just put parentheses around it, and now I mean the skolemized version, right? This is notation that Kohlenbach uses in his article to talk about the assertion that some functional exists, and I'm a fan of this, right? It's very convenient to be able to still distinguish between the two, but have them look so much alike, right? So the parentheses just mean, oh yeah, we're looking at the skolemized form. Okay. So as I was saying, this base system that Kohlenbach set up, which he calls RCA Not Omega, right, includes functionals of all finite types. So for example, things that take strings to natural numbers, like a realizer for LPO, right? Or also things that would take an infinite string to an infinite string, right? These are simply objects in the theory now. And if we're going to talk at all, and I'd like to talk a little bit about a proof in RCA Not Omega, so I need to tell you something about that proof system. It includes restricted induction again. We have some primitive recursion. It's actually primitive recursion on the natural numbers, but you can have set parameters, right? It allows lambda abstraction, so we can extract functions in that way. And naively, it's actually kind of like working in just RCA Not, right? RCA Not, naively we said if it's a function and you can compute it, you've got it, right? And here, if it's a functional and you've got it, but and you can compute it, then you have access to it. So I think you can carry out a lot of these proofs. I mean, if you do all of them in huge detail, actually listing out the primitive recursions, it's just as unpleasant as it is working in second order arithmetic if you write down all of the details. So thinking about these more computability theoretic arguments seems to streamline things. Okay. So this principle of LPO as a Skolemai's functional existence statement actually makes a pretty good ACA Not analog in the higher order reverse mathematics setting, right? So here I've written that down again, right? We already wrote down this statement about LPO, where essentially we're just asserting the existence of a realizer for LPO, right? And this is exactly the same as what Kohlenbach describes as exists to, the statement exists to, right? The functional that we're getting here is really like Kleini's E2, which I think is why Kohlenbach picked this notation, was to harken back to Kleini's functional, right? And the interesting thing here is that when you tack this on as a new axiom, you actually get a conservative extension of ACA Not for pi12 formulas, right? So this reference is an article by Sakamoto and Yamazaki that you'll see in the reference list, and they have a discussion of this argument for why this is a conservative extension, right? So that's LPO turns out to be like ACA Not, okay? And so then you say, well, LLPO probably, this is going to be very dull, and it's going to be WKL Not. That's what anybody would expect, right? So it's not. So it turns out that when you're working in RCA Not Omega, the functional existence statement for LPO is equivalent to the functional existence statement for LLPO, right? And you may not find that surprising, but it like woke me up in the middle of the night. I was really completely surprised by this. So I'd like to say a little bit about the proof of that. And what I'll do is talk, first of all, about the interesting part of the proof, which is how the devil do you get LPO out of LLPO, right? So these statements are really just talking about the existence of the realizer. So we'll work in the base system and suppose that we have a realizer for LLPO. Okay. So I want to look at the function, the input that consists of an infinite sequence of ones, right? And as a case, I'm going to suppose that when I run that through my LLPO realizer that I get 0 out. I know that I might get 0, I might get 1, right? I have a specific realizer here. So I'll get one or the other. And we'll handle the case when this is 1 in a few minutes. Okay. So we have this realizer that gives us 0 on 1. So we're going to define a sequence of inputs, a sequence of LLPO problems, right? And I'm going to call these the G sub n's, right? And basically G sub n is going to put a 0 in the 2n plus 1 position, right? And a 1 every place else, right? So each of these GNs has a 0 and the first and only 0 appears in an odd position. So when I run it through the LLPO realizer, I get a 1 out every single time, right? So if I looked at the limit as n goes to infinity of the realizer applied to the GNs, well, I'm just getting 1 every time, so that limit's going to be equal to 1. But if I look at the limit of the GNs, I'm kind of scooting the 0 down further and further down the string. And so in the end, in the limit, the string turns out to be the string of all 1s. And if I apply the LLPO realizer to that, I get 0 because that's what I'm supposing. I'm in that case, right? And 0 is not 1, right? So this tells me that the LLPO realizer is effectively sequentially discontinuous, right? Now, Kohlenbach would just call this sequentially discontinuous, which is a good thing to call it. And in his paper, he has this proposition 3.7, where he says, if you have a sequentially discontinuous functional, then you have E2, right? You have LPO. And that's the short version of the proof, right? You're just done there. We only handled one case. So if this turned out to be 1 up here for this realizer, then make all of these guys even, and that's going to swap 0 and 1 here, and that's the other case, right? So this is all right, except, well, it's applying this proposition, which unless you happen to look at that article in the last week, you probably don't know what's going on there. And the interesting thing is that the proposition is actually based on Grillos trick, right? And Grillo wrote this beautiful article about functionals that have effectively sequential discontinuities, right? And so we can replace the use of that proposition by actually going through and imitating Grillo's proof, right? So we're going to apply Grillo's trick, right? So the way that works is, suppose that you have F, right? So F is the string of all 1s, right? And we have the GNs that we've computed, right? So I'm going to think of the GNs as having the first 0 in some odd location, assuming that my realizer for LLPO is giving me 0, okay? And then I define a new functional in the following fashion. So the functional is supposed to take an input of a string, and then it's going to output a string. And I'm going to tell you how to calculate the jth element of the output of that string, right? And we're going to make it 1 if we haven't seen a 0 so far in our input string, right? And then if we do see a 0 at some point, then rather than continuing to write 1s, I'm going to switch to whatever the gith sequence was in my construction, right? So if my function, my input function, is an infinite sequence of all 1s, right, then I'm going to be in this top case all the time. And when I apply my functional, I'm just going to get that same sequence back, right? And if I'm in the case where I is the least value such that h of I is equal to 0, then when I apply j to h, I'm going to get gi out. So whenever I apply j to something, I either get one of the gi's or I get one of the f's. right? So this tells me that that sequence H, my original sequence, contains a 0 if and only if, when I apply the LLPO realizer to JH and F, if those are different, then H contains a 0. If they're the same, then H does not contain a 0, right? So we can use the realizer for LLPO and this new functional J to compute a realizer for LPO. Now, here's the situation, right? In this construction, the assumption was that our realizer for LLPO, when we applied it to the sequence of all ones, was going to output a 0, right? If it's an output of 1, right, then we use the other construction for the GIs, which is going to change the construction of J, but it's still going to be computable. In either case, RCA Not Omega is going to prove the existence of this functional J. Okay, so that's the way that we get this. So let's talk a little bit more about this. It seems very odd that you can prove this implication in RCA Not Omega when it just runs contrary to sort of our impression of the way that things behave for Buyroute reducibility, right? And really, in a way, it's not terribly surprising because they're completely separate approaches, right? And they give us different sorts of information, right? So when we say that there's no Buyroute reduction, there's no fixed computable pre-processing and post-processing functional that can turn a realizer for LLPO into a realizer for LPO, right? But under the Buyroute reducibility situation, we require that reduction is uniform, right? That it works for absolutely every realizer in the LLPO, or every realizer of the LLPO problem, right? But when we do this implication, right, what we're actually showing is, well, if I have an LLPO realizer, then yeah, I can compute an LPO realizer, right? And that's not a uniform computation, right? When we do that construction, when we're going to construct that J functional, right, we make a non-uniform choice. As soon as we say, oh yeah, this is the behavior of my realizer, right, then our process for finding the realizer for LPO changes accordingly, right? So there's this non-uniformity in the proof of this implication. So I do want to say just a word about the other half of the equivalence, right? We were saying that over RCA Not Omega, these two statements, these two functional existence statements are actually equivalent, and we just did the reversal, the harder direction. So in this direction, does that have anything to do with Buyroute reducibility? And absolutely it does, right? So if you look at the second proof that we did of this Buyroute reducibility, so the one that concentrated on the pre-processing, right, and that was actually a proof that in terms of the Buyroute degrees, that this was a strong reduction, right? That was the algorithms there were total. One of them was null, and the other one was a total algorithm. And you can prove that those exist in RCA Not Omega, right? And then you get the implication, the proof of the implication, just by the composition of the functionals. So you can adapt that Buyroute proof, right? But not the first Buyroute proof, right? Which was a perfectly good Buyroute reduction, right? But the function wasn't total, right? And so it doesn't, that argument just doesn't translate to a higher order reverse math argument. Okay. So this leads me to the questions that kind of motivate my desire to learn more about this particular material, right? And so I have three questions, and one of them I have at least a little bit of an answer, right? So we could look at these scholomized functional existence statements, and you might say, well, we looked at, you know, LPO and LLPO, and those turn out to be the same. So maybe just everything collapses in the higher order reverse mathematics setting, and nothing really corresponds to WKL not, right? So that's not true. It turns out that there's these statements about moduli of uniform continuity that are actually conservative over WKL not. And you can look at that in Kohlenbach's article. I don't want to go into too much detail. They're based on sort of a fan theorem. Some of the statements are conservative over WKL not, but inconsistent with ACA not. I'm pretty sure that there are associated statements which are conservative over WKL not and consistent with ACA not. But then I get into sort of problems in looking at the coding or the presentation of the inputs for the continuous functions, right? So I think there's more to be learned in that area. So at any rate, we know that there's some mix, right? There's some functional existence statements that actually correspond to WKL not, right? And the question is, if you look at, you know, we have tons of things that we know are like AE statements that are equivalent to WKL not. We can turn each of them into some sort of functional existence statement. Some of them are going to be equivalent to LPO. Some of them are not, right? So the question now is, are all the others weaker, and are they all equivalent to each other? Is there some sort of higher order zoo going on here that's at a low level? It's sort of in between WKL not and ACA not. I don't have good questions or good answers to any of that. And it's kind of interesting. I mean, there are a lot of things that we know are equivalent to WKL not, a lot of combinatorial statements. And I don't know if all of those are going to turn out to be equivalent to LPO in the higher setting, or if there's some sort of a distinction. I don't have a good sense, and I don't have a good way to sort these, to figure out which ones are going to be equivalent and which ones aren't. I think there would be a pattern there, but we have so few examples at this point that we just don't know what the pattern's going to be, right? And the same sort of thing may be going on at the pi11 CA not level, right? So that corresponds to the Suslin functional. We could look there. I mean, you can take statements, AE statements out that are equivalent to ATR not and turn them into functional existence statements, and then ask, are those equivalent to the existence of the Suslin functional, or are they weaker, right? And again, here I have even less information. I have lots of questions and very little information. There's some references that would help if you want to work on this stuff. I think it's a really good idea to look at Kohlenbach's article, right? And if you want to look for more of these equivalences, Sakamoto and Yamazaki have several equivalences there. So it would be, you know, good to look at the literature before you jump in with both feet. That's it. Thank you.
Nice talk, Jeff. Any questions?
I had a question. When you said these moduli things were conservative over weak Kernig's lemma, did you mean pi11 conservative?
Oh,
what kind of conservation result is it?
I think that that's actually a pi1,2 conservation result. I think it's conservative for pi1,2 formulas.
For all pi1,2 formulas?
Yeah, yeah, yeah.
Okay.
Any more questions? Paul?
Can I ask something?
No.
I guess that was a question. I'm going to anyway. What about brackets LPO versus brackets LLPO and higher order reverse math, but with intuitionistic logic? Were they separate there?
I don't know, Paul. I'm not sure. I think they might be. That's a very good question.
Great, yeah, thanks.
Any more questions?
Question.
But can I go back to the pi1? Go ahead.
Richard, go ahead.
Go, Richard.
Can I go back to the pi1,2? What's your length? I mean, in some sense, Aca Not is a pi1,2 sentence. It's every function has a range.
Okay. So
What's the length? You got to be more. If you're doing higher order functionals, you quantify over functions. And so every function has a range as Aca Not, sort of.
yeah.
And that's pi1,2 in that language.
Right. So yeah, my problem here is, yeah, Kohlenbach's principle, which he refers to as MUC, which I think is actually just an abbreviation for modulus of uniform continuity. So this is on page 293 of his article, right? And the principle that he's looking at is the existence of this fan functional, okay? And he says that the existence of the fan functional is conservative over RCA Not 2 plus WKL. So that would be for formulas of second order arithmetic. That still isn't going to address your concern.
Well, maybe it's only set quantifiers. I mean, something is.
Yeah.
Okay, no, I mean, I see.
Yeah. I think
I'm sure he means something. I just don't.
Right. I think it's a conservative for second order statements, and then it may actually be necessary to restrict that some, but I don't see the restriction here.
Okay.
Okay, so my question was about, I thought your point about the totality of the forward and backward functionals was very interesting, and I was wondering if you looked at any formal connections between this and broadcast. Like I think broadcast has this notion of total Buyroute reduction.
There's I think there's a link there, right? I do think that these two things are connected somehow, but I don't understand exactly the connection there, and partly because in Buyroute reducibility, and even in the total continuation for setting in Buyroute reducibility, you still have that extra uniformity that's just not in the higher order reverse math setting, right? So yeah, I think the higher order reverse math setting seems to collapse some things that wouldn't get collapsed in other settings, right? But it's not collapsing everything. It's just some stuff. And I don't have a good grip on what's getting collapsed.
Right. Cool. Thank you.
More questions? It's what happens in the past. I turn off the recording and there's always more questions. So I'm just going to wait a little bit.
So I think I'll take back my problem. So if they prove the inconsistency of Aca Not and Aca Not is a pi 1,2, then they're proving a sigma 1,2 formula, which the conservativity wouldn't apply if it's pi 1,2 in the right language. So I was just trying to make sense out of how close this was, and so it's okay.
Yeah, I've tried to work a little bit more on the details on that, because I would like to have like a modulus of uniform continuity functional, right? You throw in your continuous function on the closed unit interval or something like that, and it spits out modulus of uniform continuity, right? So you look at a functional like that and you say, okay, so how strong is the existence of that functional? And I think that you can derive the existence of that functional from Kohlenbach's MUC principle, and that you can carry out that derivation in either the case where the continuous function is presented just as a function, which can happen in the higher order setting, or as a continuous function code in the traditional reverse mathematics setting, right? And then I was thinking, well, if I have these two different versions of this functional, can I derive one of the functionals from the other one? And the answer to that is, well, can I derive it? No. Can it be derived? Maybe. Right? So yeah, I think there's work to be done there.
All right. I think we've had enough questions. So let's thank Jeff again.
Thank you very much. Thank you all for coming.
Yeah, normally I'm going to stop recording.